in the equation 14.4. So we got the 13.3 and then identify that with the generating function expansion and call that coefficient, the square bracket, as the Bessel function of all the n for positive n. But there's a difference in the limit for the original expression is like the square bracket within 14.3 is like that. So you have this summation. The sum over S is sum over S from maximum of 0 and minus n. For negative n, you just sum over 0, right? And then to infinity. And summing minus 1 to the S power. And then n plus S factorial. S factorial. X over 2 to the power of n plus 2s. Okay, and now for base of n, for positive n, that you just set that to 0, right? And because that's this. So comparing 0, and if for positive n, this is smaller than 0. So it's summing from s from 0 to infinity. So that would be 14.4. Now for n is negative. For n is negative, then it's more convenient to call it j minus n with positive n. So if this n is just the negative of this n, right? And so if n is positive, this is negative, then the summation will be summing from negative n, but negative n is a negative value. N is negative value, so it's negative of negative is becomes positive, right? And so you're summing s from, right? So summing from minus n becomes n, right? Because the sum maximum of minus n is positive, but we are now calling n is positive. It's a little confusing, but we're basically changing from this expression to this expression, n changes to minus n. Okay. So you have to think the same, except that n becomes minus n, so s minus n. So s factorial 2 becomes minus n plus 2s. Right. So that is for negative order. So minus n is positive, minus n is negative. So for positive n, so this is now changing to 0 to here. This is n is greater, and including 0 also. 0, you apply that also. So this is n is still positive. N is still positive here. And for 0, then this actually the same. The two actually the same, right? We set n equals 0 to 2, right? And now the trick is now we do a shift so that it doesn't start from n. It actually starts from 0. And so to make so instead of summing over s, we can do it in 2 steps. So instead of shifting it, it's sometimes difficult to see it in 1 step. So we call the s prime is s minus n, right? Doing so s is start from n, the s prime will start from 0. Okay, that define that as s prime is from 0 to infinity, and now you have minus 1. S becomes s prime plus n. Prime plus n. S minus n is s prime factorial, and s is s plus n factorial. S prime, this is s prime. The s is s prime plus s. Right? And this is x over 2, and minus n plus s is s prime plus n. So 2s prime plus 2n. And you combine that with this one, 2n minus n is just n. So cancel that off n. Okay, so now we see that this actually is of the same form as this, except there's one factor, there's a minus 1 to the n power. Other than that, this is exactly the same. Just two. I mean, other than s becomes s prime, but that doesn't matter. This is just a summation index, so you can call it whatever you want. So just you can identify that as minus 1 to the power n. Okay, and so this is so this shows that j minus n is proportional to j sub n, so they are not independent. The two they are proportional to each other, so they're not linearly independent. And so later on, we need to find another solution of the Bessel function for integer n, for integer order, and that is called the Neumann function. That we'll define that later. But this is just for integer n, and we derive this from the integer n. We derive that at least in this section. We divide this series solution using the generating function, but the generating function is defined for integer n because we are doing a power series expansion to the integer order of t. We remember the generating function, so the coefficients are this j sub n, and so that by definition is for integer order. But the same expression, we show that this is the same as the power series solution for the Bessel equation that we got from the ODE chapter. But in that chapter, the Bessel equation actually for a general order. So the n in that equation, instead of minus n squared, you can write minus u squared. So any real number square, and actually you can extend it to complex number also. But this series solution actually gotten from the same the series solution without the restriction of integer n. Okay, but so this process is basically for integer n. We show that this is the same as the series solution that we got for an arbitrary n, so including real n. Okay, so that is that. So in this case, we go back to the series solution that we got. So it's exactly of this form, but for a general order, you can say j nu. So instead of calling n calling nu, just to indicate that it can be any real number. So we have exactly the same form. Yes. Now, if this is n is a real number, or you change it to nu, this is a real number, then we cannot use the factorial function because that's defined for integer. But we can just use the gamma function, because you remember that gamma function for integer n plus 1 is this n factorial. Right? This n, we can use that And we can convince ourselves, going back to the series solution, that we can represent this the series solution using gamma function that we just learned instead of the factorial. So that changed to compare this with that. So you can change that to gamma, and n becomes nu plus s plus 1 for this one. For s is a summing over an integer, that's fine. And so this is over 2 nu plus 2s. Okay. And so that is for real order. So if we want to distinguish from these two cases, you can say it's a new real number, real number, right? And but new is not new doesn't belong to it to integer, right? And in that case, then this relation will not apply. So we derive that for integer n, but this expression is just for non-integer nu. And in that case, they're actually for the same nu, you can have positive nu and negative nu. So if you choose negative nu, then all you need to do is just change into negative nu, and everything's still defined. The only thing is that if this is negative, you have a negative nu and nu is negative, and nu is positive, negative nu becomes means that j to the negative nu order of j is singular at near x equals 0, because this becomes a negative power, which is fine. So just that function's behavior in the inverse order near the origin. So that's a singularity at x equals 0. Okay, so and for this case, you have two linear solutions for the same nu. And remember that in the Bessel equation, you actually have nu square in the equation. So the same equation you have two linear solutions. One is positive nu, the other is negative nu. So that satisfies the same equation with the same nu square. Okay, so that's fine. All right, so you can recover. Actually, you can recover this too. I mean, although we're saying that explicitly, we don't have that because, in particular, you have this gamma function. And you know that gamma function, negative integer is singular, negative integer and 0 are singular. So you don't want that. But if you take the limit of nu goes to integer, actually you can recover both cases. Just like what we did here. So, so that is all the series solution. Okay, and it's okay up to here. It's not too difficult to divide this.